refraction. It will be more or less a revisit to grade, what do you call? It will be a revisit to grade 10, but some more concepts, okay, as we keep on understanding. Let's see how much we can cover today. Okay, so shall we start? So I start with refraction. Settle. Okay, refraction. Now let's get into grade 8 as well as grade 10. Refraction in crude language just means bending of light. Bending of light. Okay, refraction stands for bending of light. And when you say bending of light, then the question says, my next question would be where does this bending of light happen? Now the bending of light will always happen at an interface. Interface is like a line of control. Okay, it's an interface. Interface of what? Interface, the interface between two transparent medium. Okay, and then we'll draw diagrams and we'll understand it properly. So it's bending of light. Where does the light bend? The light bends at the interface between two transparent medium. And what is the speciality about this medium? The medium should differ in their optical density, not mass density. Huh, beta? Not mass density. Mass density is mass density per unit mass. Mass density tells you how heavy something will be. Optical density tells me how obstructive am I to the propagation of light, right? I may be lighter. Now please understand, there are some tongue twisting words out here. I may be lighter. So let me just give a small example out here. When you use paint, you use an oil which is called the turpentine oil, right? And let's say we compare turpentine oil with water. Now, obviously, oil will float over water. So turpentine oil has a mass density which is less because it's halka, light. However, when you see the optical density, turpentine oil's optical density is more than water. That means mass density and optical density have no correlation. They just sound alike. They just sound alike. They have no correlation. Is this much thing clear? Right. Mass density tells me how heavy I can be. Optical density is going to say how much am I an obstruction? How much am I like a traffic road for light as a vehicle to maneuver on my roads? Okay. So it is the bending of light between at the interface between two transparent medium, and the medium should be such that they should differ in their optical density. So if I take a basic example, if I just take a basic example, so let's say I have wait. So let me make this a little bit smaller so that I can use the board. Okay. Fine. So let this be here. Okay, fine. Now let me say that. So say this is an interface. When I say interface, imagine that on one side you have a transparent medium which is different from the other side. One of the best example would be to take air on one side and say water on one side. Okay, we're not being very specific now, and I say let this be my medium 1 and let this be my medium 2. Okay, let this be medium 1 and let this be medium 2. And what I'm doing is that I am partitioning this. Okay, and let this be say medium 3 and let this be medium 4. There are two separate things that we're trying to say. Is this clear? Okay. Now what happens here is 3 and this is 4. Okay. So I take a ray of light which is incident on this medium. Whenever a ray of light is incident on a medium, then what happens is some portion of this ray of light will always be reflected back. No questions about it. Okay. Some part is reflected back. So let's say this much is reflected back, right? So in order to show this reflection, I should also have my normal at the point of incidence. So this is my normal at the point of incidence. So this part is reflected back. That's not our point of study in this part of the chapter. We're going to study what happens next. Okay. And then another part is transmitted through which undergoes refraction. And it can be that it suffers bending. It suffers bending. Okay. Here we would say the angle that the incident ray makes with the normal is known as I, and this is R. Okay. I will be known as my angle of incidence. Angle of incidence, and R will be known as the angle of refraction. Refraction. Right? So we'll be studying it a little bit in a manner in which we are more advanced than what we were studying in what you call grade 10. Okay. So let me say this is medium 4. Sorry. It's medium 4. I'm trying to draw one more diagram out here. Let's say this is my incident ray. Okay. And I have my normal out here at the point of incidence. And obviously, a portion of light will be reflected back. That is not my concern in this part. And this is my. So here, I'm calling this as, say, this is diagram 2. I'm calling this R2, I1, R1, and this is my I2. Fine, children? Okay. So R is my angle of refraction. Obviously, I have got an I1 and an I2. So we're going to now see on case 1 and case 2. Okay. Let's see case 1 versus case 2. Case 1 versus case 2. Now, if you look at case 1, if I look at case 1, the observations are that the angle of incidence I is more than the angle of refraction. Right? The angle of incidence is more than the angle of refraction. That means my refracted ray bends towards normal. Right? Bends towards normal. And if I look at case 2, I find that my incident ray is smaller than the refracted ray. That is I1, R1, I2, R2. So I say that the refracted ray bends away from normal. Bends away from normal. Okay, bends away from normal. We still, I'll come to those denser and rarer part. I just want to cover one more thing. By now, we also know that the speed of light, if we see the speed of light is always the wavelength multiplied by the frequency. Okay, the wavelength multiplied by frequency. And frequency does not change as long as you don't change the source. Obviously, the sun has been for so many millions of years giving us sun rays. I don't expect tomorrow some new celestial body to be lighting our universe. Okay, so not universe, our planet. So it would be the sun itself. So I'm not paying that much attention on frequency, which means my speed of light is, if some parameter changes with speed of light, it can be also in this whole ray optics refraction, whatever we study, whatever parameters like say refractive index or whatever comes, if they are related to speed of light, we can say they are also related to wavelength, because the frequency is constant, right? Is this much understood? So this is some additional thing where frequency wavelength will be playing a decisive role. Now we go back to our discussion. And we say that the refracted ray bends towards the normal, and here it bends away from the normal. Now just try to understand, children. This is what I used to say in grade 10. You are coming with a little bit of a speed. I used to say this is like somebody who is running from playground to the school bus. And as soon as you enter the school bus is already crowded. Can you run with the same speed? No, you can't run with the same speed. So you start facing a lot of traffic. So what do? Your energy goes down. Speed goes down means it's like anecdotes. It's like energy goes down. And whenever your energy goes down, you need a support to lean on. So your support is normal and you start bending towards the normal, right? And this is typically, like as we say, the crowded shuttle service in an airline. Everybody is crowded, and once you open the door at the arrival place, then it's free space. So people start picking up their speed. And when people pick up speed, they're all with energy. And once you're with energy, you don't like to look for anybody for support. And right? And you just say, who are you? I don't know you. And I can manage my own. Let's like a child coming down from a crowded bus. And this is the playground. And the child starts running, mama, and that's it. Okay. So we say the refracted ray bends away from the normal and it bends towards the normal, which means that if I look at medium 2, medium 2 slowed light, right? It slowed down the light, right? And if it has slowed down the light, it has to be optically denser than medium 1. Children, is this concept clear now? You have slowed down the light. That's why the ray of light did not have so much of energy and it bent towards the normal. Arjun, clear this point? Okay. Now, if you look at case 2, here we will say that medium 4 enhanced the speed of light. Okay. So in this case, it has enhanced. Now, these are all comparative. Okay. When you say he's a good boy, the question is that with whom are you comparing him with? He's a good boy, so somebody has to be a benchmark. I call this a rarer, denser medium because it is more denser as compared to this. And now this fellow is no more denser. This fellow is now allowing light to pass at its full speed. That means this part was more denser, right? But we have to talk about this one. So we would say, use the opposite of denser. We would say speed of light, enhance the speed of light. So we will say that this is a optically rarer medium. Optically rarer than M1. Children, are we fine with optically denser and optically rarer? These are very, very subjective words. Whenever you say optically rarer, in comparison to what? 2 is denser as compared to 1. 1 is rarer as compared to 2. 4 is rarer as compared to 3. 3 is denser as compared to. So I have written M1. It should be M3 actually. Is this much understood? Okay. Now let's understand why this refraction happens. Actually, this is one ray of light. But if you actually go back to your grade 10, you would see that let's say this is my interface. I don't have only a single ray that is coming, right? I don't have a single ray that comes. So the rays come in. This is one ray, right? And let's say this is the entire thickness of the interface. I would have one more ray coming in this manner. So by the time this ray undergoes, it takes some more time. Sorry. The second ray will take more time to come down. This is causing you the. So if we talk now about refraction, we said a refraction, mathematically we will see a refraction is, if I write in mathematics, we'll say it's a function of bending. Yes or no? Yes. Bending is again a function of the difference in speed of light. The difference in speed of light. And that's where the story will be clear. And the difference in speed of light is a function of the difference in optical density of medium. I hope it's getting clear now. So if you have two mediums which are optically whose optical densities have a difference in terms of one being more rarer than the other or one being more denser than the other, then in that case the light that travels through the interface of these two medium will have a change in its speed. The speed of light changes, and if the speed of light changes, the light bends, and that phenomenon is known as refraction. Clear hai abhi? You will be able to explain everyone what is refraction all about. Refraction is the bending of light. This will always happen at the interface of two medium of varying optical density, and that varying optical density is responsible for the change in speed of light. So the speed of light changes. In other ways, we just had a talk right now. If I don't want to use the word speed of light, I can also use a word called change in wavelength. Because if you differ the wavelength, the speed automatically gets, just see, the speed of light C is given by the product of the wavelength with the frequency. If this fellow is constant, then the moment you tweak this fellow also undergoes a change. So don't only think that if there is a change, because till grade 10, the concept that used to be in our mind was, if there is a change in speed of light, there will always be bending. Now in grade 12, we'll say if there is a change in wavelength, there will also be refraction, because a change in wavelength will ultimately result in a change in speed of light. Is this understood? Okay. All right. So we go to our next section, where we will now concentrate on what is known as laws of refraction. So the laws of refraction are simple. The incident ray, okay, the refracted ray, and the normal all lie on the same plane. All lie on the same plane, which is very easy. All lie on the same plane. The second one is known as a part of the laws of reflection, is Snell's law of reflection. Oh, sorry, refraction. Snell's law of refraction. But Snell's law of refraction, now you are getting into grade 12, will not be valid always. We will see. This law will be valid only to a particular range. Snell's law says, okay, now let me once again make my diagram so that it becomes clear. So children, please understand that whenever refraction is taking place in grade 10, you have seen the diagram that there's an incident ray and it cuts across here. Doesn't mean that there is no reflection. Reflection will always be there. But since you are studying refraction, you are more interested in seeing this part. Okay, so let me make this diagram, and this is my normal. Sorry. So this is my normal, and this is my incident ray, and this is my refracted ray. Okay, now I start naming them. So this is my angle of incidence I, this is my angle of refraction R, and obviously this is medium 1 and this is medium 2. This is medium 1 and this is medium 2, right? So Snell's law of refraction. Snell's law of refraction tells me that the ratio of the sine of angle of incidence to sine of angle of refraction will always be constant. Okay, will always be constant. Now there will be a lot of confusions here, so let's get this cleared now. Sine of angle of incidence to sine of angle of refraction will always be constant, and such constant will be known as the refractive index. We call it the refractive index. Okay, now don't use the word refractive index of the medium straight away. Okay, so we will say refractive index of the medium Now when you use the word refractive index of the medium, then this medium means where light has traveled in. Means refractive index of the medium means, in our example 2, where light has traveled in from the interface. Okay, so statement is not yet complete. It says it will be constant and it will be known as refractive index of the medium with respect to the medium from where light was incident upon, right? So in this case, I will call this as, this medium would be, okay, where light has traveled in from the interface, and here we say with respect to the medium from where light was incident upon, then that means that this medium was above the interface. Now again, children, above the interface does not mean, now listen, I have written above the interface because incidence is happening from here. If the incidence was happening from here, then it is below the interface. Just understand that. We will always say refractive index of the medium to whom the light entered with respect from where you entered. Okay, with respect from where you entered. So in this case, this is medium 1. Okay, so this is a constant and we write this constant as eta. Now we'll see how NCERT writes it, and we will also see how we have learned it so far till grade 10. In NCERT, we'll write it 2 followed with 1. It stands for 2 with respect to 1. Always remember, this has to be the incident medium, and this is the refracted ray medium. This is the incident ray medium. This is how we do it. I'll create some confusion cases also so that you understand. Refractive index eta 21. This is how we write it in NCERT. Will be using this. Now there is nothing to be confused about. Some books may also write it in this manner. Eta 2, eta 2, respect. And in Indian culture, respect, the person whom you give respect, you make him sit at a higher position. So with respect to 1. Eta 21, this is same as writing eta 21, so that you don't get confused. Because your NCERT is following this nomenclature. Some books may follow this. How to remember this? 2 with respect. Jisko respect dete hai, you make him sit. Respect. With respect, please take the higher seat. Okay. I would not like to go to the next slide, but I would like to make this smaller because let the discussion be here itself. It makes you understand things better. इसी को छोटा करूँगा. Okay. Right, fine. Keep your eyes on, keep your mind on this discussion as we go ahead. So I said that sine of angle I, not me, Snell says, sine of angle R is a constant which is known as eta 21. Means whenever you write this, please remember that your drawing has to be in this manner. This has to be 1. This is your normal and this. So this is I and this is R. This is the drawing. The drawing could also be like this. This is the normal. In this case, this is my I, this is my R, this is 1, this is 2. I hope all your ambiguities in respect to 1 and 2 have been answered now. Is there any issue? So whenever you write, see, we are measuring the refractive index of 2 with respect to 1. Okay, so sine of 1, 2 with respect to 1. Now, this will always tell me something called refractive index. Okay. Now, there will be 2 scenarios now. So, one is our medium from where the light is getting incident upon. Okay. So, I'll be talking in terms of 1. If 1 is air, that means there's something like this. Okay, means this is air and this is some medium 2. If 1 is air, then this refractive index will be known as absolute refractive index. And I would write it as only eta 2. It is same as writing as eta 2 with respect to air, but I will write it as eta 2. This is known as absolute refractive index. Because whenever you are comparing, refractive index is a unitless quantity. Okay, this quantity does not have any unit, no unit. And it is the comparative statement. This boy is good. This boy is good with respect to whom? With whom did you compare him? So the benchmark that we take is always air. If you are comparing anyone with respect to air, mind you, the light should be coming from air and then entering into your medium, not vice versa. Not vice versa. Okay? If the light is coming from air and is entering into your medium, then the refractive index of your medium with respect to air is no more called with respect to air. We straight away say refractive index. We call it the absolute refractive index. However, the confusion appears when, in general tone, this will be also known as refractive index of medium 2. They will just write the word refractive index of medium 2. You should understand that this is the absolute refractive index of medium 2. For example, if you Google today and you try to find out the refractive index of glass, they will give you a figure like 1.33. Question arises. Glass was on this side. My friend, what was on top? Turpentine, plastic, acrylic, air, air. Because for all other things, I will have so many values for glass. So in Google, so many values should come out. But we take one standard. So when we say what is the conversion rate of the Indian rupee, the standard is taken with the US dollar. Right? But there are so many dollars. So the standard is taken as US dollar. So similarly, the standard will be taken as air. And all refractive index data that you get are all when they have been compared with air. At that time, physics-wise, I call it absolute refractive index. But going further, you will see the word written refractive index of 2. If it is not mentioned with respect to what, you should understand that it is with respect to air. Like, for example, we keep writing in differentiation and all log, log, log. There's a difference. Log can be with respect to base 10. Log can also be with respect to e. If this is the case, then this is known as natural logarithm or ln. That's why in India, we are habituated to write log, log, log. We don't write the base. We presume that the other person is understand. So in good books, you will always see ln written. Ln written means no more confusion. ln stands for log natural. That means the log is with respect to base e. This was just for your understanding. So similarly, we will be using when you use the word refractive index. Now question comes is, sir, what happens when it is if one is not air, and it can be any other thing. If one is not air, it can be any other thing. It can be plastic. Then we call it relative refractive index. If it is not the US dollar, then the Indian rupee has different conversion rate with respect to what dollar you're using. Singapore dollar, Australian dollar, Zimbabwean dollar, in that manner. Got it? It is called the relative refractive index, and this will be very case to case based. You will get different values. Case to case based, I will get different values. Is this concept clear or not? Otherwise, you will jumble up in numericals. Understood? Right? So if they give you a problem saying the refractive index of a medium is say 1.2, so you should always understand that if the refractive index of a medium is 1.2, that means they're calling about absolute refractive index. If you don't see two numbers along with this, that means it's absolute refractive index. Okay, so going further, I'll just give you an example. Say my medium is glass. Glass can be compared with respect to many things, say oil, water, glycerin. I hope you are understanding. Ray of light is coming from glycerin and entering glass. In this case, we will write it as eta glass with respect to oil, or it can be eta glass with respect to water, or it can be eta glass with respect to glycerin. All will have different values. So we need a standard. So the standard way is we will take glass and we will have, we will have it with respect to air. So it will be eta glass with respect to air, which will be same as eta glass. That's all. This is absolute refractive index. This is relative refractive index. And if you're a little bit confused about how light is entering, light enters in this manner. This is how light will be entering. मुझे नहीं लगता अभी आपको कोई डाउट होना चाहिए. Fine, right? So in grade, what do you call? In grade 10, we also saw something like this, that the refractive index, I'm writing it in grade 10 manner, 2 with respect to 1, which in grade 12 we are writing as 2 with respect to 1, is also equal to the velocity of light in medium 1 to velocity of light in medium 2. Have you understood? Velocity of light in medium 1 with respect to, again, always remember where the light is coming from, that's velocity. Is it fine? I further do something. I divide the numerator also. Is it fine? Okay. So I can write my next step something like this. Now just concentrate. This by this will make 1. Do you agree? This by this will make it 1. Now this is also a scenario. What is this scenario? Velocity is being, the light is being incident with a velocity from a medium from V2. This scenario is what, children? Just look at this ratio, okay? Just look at this ratio. Isn't this ratio like this? Medium 2, velocity is 2. Medium 1, and I'm saying velocity is V1. Correct? Can you now assign a ratio to this? I would say this is refractive index of 1 with respect to 2. Same thing. So I can write this as, this is one important finding that we have. You can also do it like this, sin I by sin I, sin R by sin I, sin R by sin I. So this is a better way to understand. Okay. Okay. Now if, second discussion, if incident ray came from air, incident ray came from air, that means how should be our diagram? Air versus any medium, say 2. Air versus any medium 2. All right, this is the incident ray. Right. Now, sir, how do you know that this should be bending this side and it should not bend away? That's the next question. So how do you understand this? If incident ray came from air, then I would write the refractive index of 2 with respect to 1. 2 with respect to 1. In 1, I will write what? 2 with respect to air, which is nothing but refractive index of 2, because the absolute refractive index. Is this clear? This should be equal to speed of light in medium 2 and speed of light in medium 1. But the speed of light, medium 1 is air. In air, we call it c. Have you understood? And light cannot, the max speed of light, the max speed of light is c, which is equal to 2.99 roughly into 10 to the power 8 meters per second. इससे ज़्यादा speed हो ही नहीं सकता है. The maximum speed is when you are coming from air. Do you agree? That means this ratio should always be greater than 1. Right? That's the reason if you go and see the refractive index of any medium, it will means absolute refractive index. So get your concept correct. If you're saying absolute refractive index, that means light is coming from air. If light is coming from air, then on numerator I have the speed of light in air, which is the maximum speed. Nobody can attain this speed. So the denominator will always be lesser than the numerator. Such ratio will always be more than 1. Now you can Google and see refractive index means absolute refractive index of anything. You will always find that their values are always more than 1. If the absolute refractive index is found less than 1, that means you have discovered something in which light travels faster than air, which is not possible. Are you understanding? But if we try to do the opposite, let the light come out from glass and then get into air, the speed of light in glass will be less and the speed of it is coming out. So incident part will be less, denominator part will be more, this fraction will be less than 1. But in that case, that is not absolute refractive index. Then you are trying to find out, refractive index of air with respect to another medium. I hope if you are, can I just change the slide at this point? Okay, I'm just, don't get confused. I'm just saying like this. Say I have a medium 2 out here and this is air. So let's look at our diagram. Medium 2, the speed of light will be less, right? And air, the light will go like mama, the child will run away. So the child runs away this way. So this becomes I and this becomes R, right? Now this is speed of light and this is speed of light. Now you are trying to find out, what, children? Refractive index of air with respect to 2. Right? We won't have any other name, but this is because this is air with respect to 2. Respect means jahan se aata hai. So this will be what? Speed of light. And this ratio will always be less than. So air's refractive index differs upon with whom you are trying to compare. Tell me one thing, is it clear now how to relate refractive index with how light enters, how light gets out, right? So the summary of our discussion so far is sine of I upon sine of R. Snell's law is absolutely fine. This is a constant. And your book will always write it as eta 2 with respect to 1. Don't get very much don't blindly follow this. You should know how to decode this. It means I am trying to identify the refractive index of 2 with respect to 1. Light is coming from 1 and then the light is entering this side. Now the question is, if you see a value which is now let's say MCQ type questions, okay? Now this is I and this is R. Let's see some scenarios. If the value of eta 2 1 is greater than 1, if it is greater than 1, right? That means the speed of greater than 1 means this value is also equal to speed of light in 1 by speed of light in 2. This is greater than 1 means V1 is more than V2. Understood? If V1 is more than V2, if it is greater than 1, then the first thing we'll say 1 is rarer than 2. This is the first finding. In other ways, we can also write 2 is denser than 1. Okay? Then we will say another finding we can find is the incident angle of incidence will be always more than the angle of refraction. Just check. It has to be. So the fourth thing that we can say is refracted ray bends towards normal. Then we can also say the speed in 1 is greater than the speed of light in 2. So many findings. And based on this, we can create so many MCQs for you. If this ratio eta 2 1 is more than 1, that means 2 is optically denser, 1 is optically rarer, incidence angle is more than refraction, refracted ray bends towards the normal, and velocity of light in medium 1 is more than velocity of light in medium 2. Okay, let's say I say this value is equal to 1.33. Now what does this mean? This is a unitless quantity. It doesn't have any unit. So we would say that the speed of light of medium 1 is 1.33 times the speed of light of medium 2. Or we can say medium 2 slows down light by a factor 1 by 1.33 times that of medium 1. If you understood, if I am 2 times as richer than you, then you are 1 by 2 times as poorer as me, right? So that's the same thing. Have you understood? So the refractive, so what does the refractive index quantify? The refractive index is a simple number which tells me how much of obstructive is a medium. Now we are not comparing about air or anything. I'm just saying eta 2 1 is this. It means 2 is much more denser than 1. The speed of light in 1 is 1.33 times the speed of light in 2. 2 reduces the speed of light. Angle of refraction would be smaller. Light will bend towards the normal. Angle of incidence will be more. Clear? Okay. The next numeric, formula that we saw for using in numericals is eta 2 1 is also equal to 1 pi eta 1 2. I hope you know how to derive this. We've just shown you. Okay. Even if there's any confusion, always write eta 2 1, 2 with respect to 1. So this is V1 by V2, can also be written as V1 upon V1 by V2 upon V1. This is 1. This is eta 1 2. Okay. Then remember in 10th we used to say one Patal Lok formula where you used to swap one with the other. Okay, one of the refractive index will be hidden. So how to see that? Now, though there is no official way of explaining, but I'll go again by the grade 10 way. You can swap it in any manner. Just understand this. It will become easy for you. First, we will write it in grade 10 method. Eta. Right? Imagine this as below the ground and this is above the ground. Okay. 2 with respect to 1. Another eta. Another eta. Right? This 2 is 2. I can bring a 3 out here. Ultimately, you have to get a 1 out here. So this 3 should get cancelled. So I can put a 3 out here. I can put a 1 out here. Just like a jugglery, try to understand this is similar as 3 is cancelled by 3 and it's 1 with respect to 1, which makes life much more easier. That's what we actually did in grade 10. In grade 10, we used to see another way of seeing it also. Say somebody tells you the problem, give the problem in much more confused manner. They suppose give you only eta 2. Only eta 2. That means absolute refractive index. So you from your side add air is equal to, right? Okay. So we have to bring air back. Say this is something like 2 and this is with respect to 3. Then we should also have eta. Now I need 2 to be here. The 3 should come here and the air should go here. So ultimately it is same. How to read this now in your grade 12? In grade 12, we will be reading it as eta 2 1. Fine. Is equal to eta 2 with respect to 3 into eta 3 with respect to 1. This sometimes becomes confusing. This will never ditch you. As long as you know how to correlate these two. So how we will write this in grade 12? Eta 2 is equal to eta 2 with respect to 3 into eta 3. If somebody gives you this formula straight away, even if you mug up, you'll make some mistake. But here you will not make mistake. This is what I used to call Patal Lok formula. There's a Patal and there's get below the ground, get above the ground. You'll not make mistake. Arjun sir, have you understood this concept, how to apply? Because the textbook will be going in this manner and there's potential chances that you'll goof up here. So always bring it up. And this is your imaginary line. It's just like a fraction. The cancellation. Fine. Okay. Now, this is a part of your experiment also. If not in this year, it's just to be in our grade 10. Now, refraction to a rectangular glass slab. Okay. So, let's see. So, this is my first point of incidence on the normal. And this is my incident ray. Now, this is coming from air. This is coming from air. The typical 1-to-1 combination. air, glass, air. 1-to-1 combination. So I have my angle of incidence, and air is the rarest. That means whatever medium you have taken now, it will bend light. So let's bend it. Right? So this is my angle of incidence, and this is angle of refraction. The angle of incidence, in other words, we can say this is say I1, and the angle of refraction say R1. And then I have my next normal. Now whatever is R2 will become my next angle of, this will become I2, and this will be equal to R1. Is alternate interior angles. And then I'll get my okay. There are some things. This is known as my incident ray. This is known as my refracted ray. Now, is this not okay? This is refracted ray, can also be construed. This can also be construed as incident ray. Incident ray for this surface, the next surface. Are you understanding? I'm not, because this is some grade 10 stuff. Arjun, clear? This is incident ray for this surface, refracted ray for this surface. Again, an incident ray for this surface. The refracted ray will behave as the incident ray. And finally, this is also a refracted ray. But since you're coming back out into the same medium from where you came, the English name that we will give it is emergent ray. So is an emergent ray a refracted ray? Yes. What is the speciality? The emergent ray means the light is finally coming out to the same medium from where it was incident upon. It's a 1-to-1 combination. Okay. And I will now find as the final angle of emergence or the final refraction, which is say R2, this will be exactly equal to I1. Which makes us also study this, that if you see, whatever was the angle of incidence is same as the angle of emergence. Okay, finally the angle of emergence is same, but what has happened is light has shifted its course. Light has shifted its course, and this shift in the path of light, this shift will be known as lateral shift. Okay, this will be known as lateral shift. Fine so far? No confusion. These are great. Okay. Among some of the observation or some of the impacts or some of the things of refraction is something called apparent depth of a swimming pool or a river. Apparent depth. So this is my whatever is the river, and say this is a normal. Okay, this is the normal, and let's say this is the bed of the swimming pool. Okay, okay, more normal. Okay, we'll try to see two scenarios. Now, this is my so-called the depth. So this is known as the actual depth. What is this measurement, children? This measurement is actual depth. And this medium is water. This is actual depth. And you are observing this is air. Right? So we'll create now will create now light rays which will be coming out from the depth point. So the light rays are coming out from the depth point. This is one ray, and this is one more ray. Okay. Children, now try to apply your knowledge. Light is coming out from water, and water is what? Water is a denser medium. Coming out of air, which is a rarer medium. Denser to rarer. What is the impact you expect? Light to deviate away from the normal. So now don't get confused. These are 2 points of incidence. This is point of this is point of incidence 1. This is my first point of incidence, and this is my second point of incidence. I'm just mutating this diagram more so that you understand. So you will definitely have one normal out here. I have a normal out here, and I will also have a normal out here. Are you understanding? This is the interface now. And the refracted ray will be deviating away from the normal. And similarly, we will find one more just deviating away from. Right. And they are divergent rays. So all I can do is only produce them backwards. This is a very dangerous swimming pool that I have created, because the apparent depth has been reduced so much, the person is literally expected. And here is your beautiful eye. So you observe, and this will be known as my this is my apparent depth, not the other one, huh? This is my apparent depth. The apparent depth will be always equal to the actual depth divided by the refractive index of this medium 2, which is water. I'm writing here bracket as 2. It's whatever 2 you take. Is this understood, children? Apparent depth. Because it is theta 2 H2O, so I should find with respect to air. Now, if you want to see one more diagram, it is something like this. If you want to see it from slanted way, so say this is the rays which are coming out from the bottom. These are the rays which are coming out from bottom, right? And I'm not drawing the normals anymore. So this undergoes a refraction, so it will bend away. And similarly, the other one will also undergo refraction, so this will also bend away. Okay, both will bend away. And since they are divergent, I cannot slightly So to make your diagram more accurate, you can follow the reverse process. Now it will be accurate. Right? And that's your actual depth and apparent depth. And you will see it always on the normal, huh, children? You will always see it on the normal. So you can make your eye out here now. And apparent depth. Just fine. Almost on time. So we have one more topic called total internal reflection. If I start it now, I won't be able to finish it, and I don't want to leave it halfway. So up till here, we will conclude today. Total internal reflection is an interesting topic. You have questions that come on, applications of that also. So apparent depth is this much fine. We'll do all numericals. Don't worry. As of now, just two formulas. You had three formulas today. 2, 1 is reciprocal of 1, 2. Then you had that changeover. Then the third is the apparent depth is equal to the actual depth divided by the refractive index of the medium, whichever it is. We'll conclude here then. On our next class, we will do total internal reflection and then refraction through a prism, and we'll get insight to refraction through spherical lenses, which is actually more important part of yours. Clear? Understood?